started. Any question regarding your product 4? Homework course as well? Have you started working on any of the two? Okay, cool. If you have started working on your product 4, right? Note that there's a slight difference in the way we run the test program in this case. I forgot to mention that. The test driver actually was not used, even though it was not there, but it was not used. The real test driver is min.c. It's under min.c. Check this. Even though there's a test driver.c, just as what we did for all previous projects, the test driver.c actually is not used. The test cases, all test cases are actually in this folder, min.c. And if you look at it, I think the first test case and maybe also the second test case are easy one to deal with, in the sense that the amount of data they have is less than your memory size. In other words, you can store them in a single pass using path 0. And path 0, all that path 0 does is load it into the memory and call this queue sort, which actually there is an example for you for that code as well. You simply copy that code over, then you're done. So I think all of you should at least score 50% on this project, right? Because there are only 4 test cases. If you just do path 0 without doing any of the following, you got 50 points. And path 0, all you do is open a scan, load data, queue sort, done. Seriously, right?
I noticed there was a small bug in the example that inside of the condition it actually had equals instead of equals.
I think that's the case. So Charlie, can you do us a favor, post this as a discussion thread? Sure. Then I can comment there, and then everybody in the class can see that as well.
Sure.
Okay, thank you. If you notice anything abnormal, like bug or things like that, like do just what Charlie did, right? Like raise a question or go to the Canvas. I think the Canvas discussion forum is a really good place for us to exchange ideas interactively. And I encourage all of you to go and check out the threads, not only by me, but whoever posting over there. I mean, they contain useful information, right? All right, so that being said, let's come back to the lecture here. So last lecture we talked about query evaluation, and we stopped right here on the discussion of matching your query predicate to an index. And what we said is you can convert this, you can convert your query predicate condition to a conjunctive normal form. In fact, we all know conjunctive normal form is equivalent to a destructive normal form. So in a query engine, in a commercial database engine, they may use either CNF or DNF. You may find both cases. And CNF is essentially like that, whereas DNF is okay. And in the CNF case, and in the DNF case, okay? You follow this discussion? What I said just now? It doesn't matter which one you're using because you can always convert one to another. And furthermore, any condition, any logical condition can be can be converted to either a CNF or DNF. Actually, if you are able to convert your condition to a CNF, automatically you get a DNF expression. The other way is true as well. If you convert your condition to DNF, you will get a CNF as well. Okay? And we focus on DNF discussion. And what we said is this. An index, a tree index, because we basically distinguish a tree index and hash index, right? A tree index matches a conjunction of term, meaning that we're using CNF. That's why it's a conjunction of terms instead of disjunction of terms. If you're talking about disjunction of terms, then you're talking about DNF. Okay? It matches a conjunction of terms that involve only attributes in a prefix of the search key. Note that it is not the same as it is a prefix of your search key. It doesn't require that. It only asks for the involvement of attributes from the prefix key, from the prefix of your search key. It doesn't have to be a prefix. These two are different, right? For example, this index matches this. Why? Because A and B are attributes for a prefix of your search key. This is your search key. Your search key is ABC, and a prefix of that search key is AB. That's one of the prefixes. In fact, this one has three prefixes: A, AB, and ABC. So we're talking about the second prefix, which is AB. This condition involves, and by the way, this is obviously a conjunction term, the CNF term. The attributes are all from the prefix. Then we say this index match this condition. What happens if I swap this condition? Like B equals 3 and A equals 5, then this claim is still true because yes, B and A is not a prefix of this, which is AB, but this condition asks for attributes involvement in the prefix, but not the prefix itself. So even if you swap this index still matches this conjunction term, meaning that you can actually use this index to facilitate answering this query. Let me give you another example. What about, that being said, okay, let's just do a few checks. Let's say my search key is A, B, C. Okay, I'm going to ask one of you to answer the following question. In other, whether the index matches your search condition or not. Okay, I'm going to write a few examples, then ask you about it. Okay? Is that okay? All right. So what about this? Someone wants to volunteer? It does not match. That does match. Does not match. Okay. Can you tell me why?
It's not a prefix. The other prefixes are A, AB, and ABC.
Okay. It does not match because it involves A and C. Okay, do you follow me? It involves A and C, but A is an attribute from the prefix of A, but C is not in the same prefix. By the way, in checking this, you want to use the same prefix. You cannot use the argument, oh, A is in the prefix A, and C is in the prefix of ABC. If you use that argument, then anything matches that. Because you can always, unless you have an E here, that's not even part of your search key. Okay. Well, the example I have over there, that obviously does not match because it is not an attribute in the prefix, right? Okay? Only attributes in a prefix of. Oh, by the way, the other thing is, I forgot to emphasize one thing is, only attributes here means only those attributes the reason why B is not a match is because even though this is a prefix, right? AB is a prefix. So B, but one thing I think is subtle, which is not stated here, is that you have to, if you consider this, it has to match all the sub prefixes coming before this prefix. Do you follow me? So meaning that you have to, for B, you have to check whether B and this. So you have to check all the prefix leading to the first prefix containing this attribute, because otherwise any attribute is a subset of the prefix that containing all attributes. Do you follow me?
So are we saying it matches if some ordering of our search term matches a prefix?
Yes. If you're that's cool. That's a critical observation because we are talking about CNF. So any ordering of the term gave you the same CNF back. In other words, this is the same as. That's why you can do that any ordering trick. And that's the reason why people actually use CNF, because that makes you reasoning easier, because you can order them any way you like in the process of finding search.
And this is all because the tree is sorted so that it's first sorted by A and then by B.
Exactly. That's the reason why. Tree is the reason for this observation we have on the slide. It's precisely because tree is sorted, the data entries in a tree index are sorted by the search key. On the first attribute first, then the second attribute, then the third attribute. In other words, data entries in a tree index are sorted by the prefix in that order from your search key. In the prefix order of your search key. That's the precise way of describing it. Okay? Now, next, what about hash index? Well, hash index, the answer is actually quite straightforward. You must have all attributes in your search key. All attributes meaning that all attributes from all terms in your conjunctive normal form. So attributes from all these terms, attribute from all these terms must be found in your search key in order for the hash index to be useful. Okay? That being said, remember what I said earlier, what I said so far and on the slides, these are some basic rules. It doesn't mean though, it doesn't mean you have to go with these rules all the time. I'll give you an example. Let's say I have a hash index. I have a hash index ABC. Okay? And my search is, so that's it, the hash. My search condition is A equal to 5 and C equal to 10. By our discussion, this does not give you a match. But can we still use this hash index or not? Victor says yes. Okay. How do you use the hash index in this case?
In this case, we would find all the ones that match where A equals 5, and we can look through all of those to check for C equals 10.
Well, but the thing is, you cannot, right? Because your hash is on these three values together. How can you find all the matches for A equal to 5? I mean, it is possible to do that, but you have to show me how to do it.
Or you could, I guess, fill in arbitrary values of B.
Arbitrary value of B. To be more precise, enumerate through all possible values of B, not arbitrary value of B. You have to enumerate through all possible values of B. So in other words, I can turn this into going through all the possible values of B. As you can tell, this process obviously will be expensive if the domain of B is big. But if you know B, let's say if you know, if B is a flag, meaning true or false, then yeah, it doesn't match, but I can still use this hash index because I only extend B to 0 or 1, assuming B is a flag, of course. B flag. repeat flag. Okay.
So can I look on the tree as well?
Okay, we all understand the hash, right? Now let's come back to tree for Daniel's question. What about tree? What about tree? Okay. Let's use the same example, right? My search key of the tree index is A, B, C. Okay? And I give you a search condition, say, okay, let's say that's my search condition. Can I use my tree in this case? By the definition we have discussed so far, this tree does not match this condition, right? Because this does not match the prefix of the tree. Does not match the prefix of the tree. Okay, so you cannot use the tree. However, if you know some knowledge about the value distribution of these attributes, you may still be able to utilize the tree. For example, there are a couple of cases, tree is more involved, right? So let me go through a few examples to illustrate my point. First of all, we notice that I can still use this tree if I simply ignore this one. Okay? I just use A equals 5 and ignore C equals 10 altogether. I can still use this because now this is a match because this involves only attribute from the prefix, which is A. And then for all the record I find using this tree for A equal to 5, I do a post-processing for C equal to 10. For example, you want to find all CS female students. What I can do is I can find all CS students first, then do a filtering step for female students. Okay? But you have to be careful. What about if I ignore this and go with this? Does this work? It's tempting to say yes, right? You ignore one and go with that. It's and. Which one you ignore doesn't matter, but it does matter, unfortunately. In this case, if you ignore this and go with this, the tree is still useless for you. Why? Because this does not match a prefix of your tree. If you want to understand the fundamental reason, it goes back to what Charlie said earlier. The tree is sorted by A, then B, then C. If you have something sorted by A, then B, then C, it's sorted by A. If you have something sorted by A, then B, then C, it is not sorted by C. Period. That's like. What about, I don't want to ignore. So one trick is to ignore, right? What about if I don't want to ignore, I want to apply the similar trick I have just done for hash, which is adding the missing B values. Can someone tell me how we can possibly do that?
So if you like the lowest value in terms of the sort order that we can take, then can you just apply that in?
Fantastic. You figure out the domain of B and you express a condition such that any B will match. For example, if I know my B is positive integers, if I know that, okay, then I can fix this by why? Because this is the same as this. If I know this. So this discussion actually is quite involved, right? So as you can tell. So what we are discussing here is the simplest form. I didn't want to go into detail because database engine actually does all of these tricks. But in order to do all these tricks, database engine needs knowledge. For example, we need to know the domain distributions. We need to know what kind of index you have. And that's what we call metadata information for your database. And database engine keeps those metadata information in a particular place. where they can look up this and use it for optimization. Okay, now let's get one more thing before I move on. We haven't discussed, we talk about, yes, we are talking about CNF, but our CNF is a simplified version of CNF where each TI, capital TI is a small TI, meaning there's no OR conditions in every single term. Okay? So it's a simplified version of CNF. You may wonder, how do you handle the general form of CNF? The general form of CNF. Follow me? I will discuss that, I believe, in a few slides. So we defer that discussion later on. But keep this in mind, right? Keep it. All right, so now once we understand this, there are two approaches to general selections. The first approach is you find the most selective access path. By most selective, this goes back to the concept I introduced in last lecture, which is selectivity of a query. More selective means you are selecting less number of records from the underlying table. Less selective means you are actually selecting more records out of the underlying table. Okay? So you select the most selective access path. What is an access path? Well, an access path is just kind of like what are the possible access paths to this lecture hall? I can go from here, I can go from here. I can go from the basement, I can exit MEB, then climb up into WB. Right? So there are many possible physical access paths to this lecture room. And this is the same concept for database query evaluation. So an access path represents one possible physical evaluation of your query. Way of, one possible physical plan of evaluating your query. Right? For example, one access path is to do a linear scan over your heap file. Another access path is to do a binary search if you know it's a sorted file. Okay, so that's the example of access path. And you want to find the most selective access path and retrieve tuples using it and apply any remaining terms that do not match the index. What does this mean? Well, what this means is as follows. Once you convert to this, conjunctive normal form. I guess it's easier to use example, right? Use an example. So let's say I have a tree index like that. Let's say I have a tree index. So my first index is AB, the tree. And I also have a hash index on this. And my condition, my query condition is, let's say, that's my query condition. Do you follow me? That's my query condition. So what are the possible access paths in this case? One possible access path is do this, using this, then apply this condition as a filtering step in the last step. Okay? That's one access path. Do all of you follow me? So access path 1. AB then C. Okay? What about another access path? Okay, to be more, I should be more precise. AB okay, now that's better. Huh? AB using this tree, then apply C on the fly. You don't even have to use hash in that case. The hash index. You don't use the hash index. And access path 2 is what? C. well, this hash index and AB on the fly. You agree? You follow me? Right? So now with this, what do I mean by most selective access paths? Well, here you are not referring to the selectivity of the overall query. Because no matter which access path you use, the overall selectivity of the query stays the same. So the most selective access path refer to the very first step in your access path. Like, is this more selective or is this more selective? And why does this make sense? Once you understand what's going on here, this makes perfect sense. Because the second step of all these access paths is the same, which is applying some condition on the fly, which is a linear cost. So the more selective you are in your access path in the first step, the more efficient the overall thing is. Okay? That explains why we do this. Okay? So there's an example of this. So let's go with this example together. Let's say we have a date less than this, and both ID equal to 5 and CID equal to 3. So suppose I have a B+3 index on date, then I can, that's one access path already, because that match my part of my search condition. I can use that, and then check the remaining ones on the fly. So that's one access path. And similarly, I can have another access path if I know I have a hash index on both ID and CID. But then you have to check the date condition on the fly. Pretty much similar to what I have here. Okay. What about if you have B+3 on name and date? Can you use this? Does that give you yet another access path? That's my question. What's your name? Al. Alex. Yes or no? Sorry.
Thinking about something else as you were.
No, don't worry, don't worry. Yeah.
What's the question again?
Will this index, if I have a B+3 index on this, that's my search key, name and date. Will that give me another access path to the query above?
Don't think so.
No? Okay, let me find something.
I think no.
You think no? What's your name?
You
Okay. You said no. Why?
because actually you are doing this indexing on the date, but the tree is sorted by name first. So it's so name is not date is not a prefix of the.
Yes. So Alex, by his explanation, so you have an index on these two attributes. So the prefix is this. So this condition is not matching your prefix. So you cannot use that to answer your query. And if you want to understand fundamental reason, again it goes back to what Charlie said. Because the entries are sorted by the name first, then date, and you are doing a range search on date, it's impossible for you to use the index to help you answer that query. Okay. What about a B+3 on date and our name? I just swap the order of the two. Now Alex, you say yes, right? Because now this will be useful for answering the search on date. What about a hash index on date and our name?
Sorry, real quick on the last example. So are we saying that we have a B tree index on day plus this other B plus tree, or both, or just one?
Whether the red B tree on date still holds or not.
Yeah.
Okay. Well, I mean, what I said applies whether you have that or not. What I'm asking is whether this gives you yet another access path.
Yeah.
So each access path is independent from the other, right? What I'm asking is whether knowing you have this will give you another access path or not. So it doesn't matter whether you have a B plus 3 on date or not.
So I guess my real question is that if you were to take the path, would they still be, what I was saying is you look at your B plus 3 index per day,
Okay.
and then you look over those entries. And I guess what I was saying is, does that really change what we have in the index on hardening?
The answer is, I think what your question is about fundamentally class index and unclass index. If you have a B plus 3 on date, and if it's the class index, it doesn't prevent you from doing another index like this. However, the second index that starts with day, you know that if that's a class index, this must be an unclass. This must be an unclass index because the record can only be sorted in one order. But if you talk about index here, let's say we talk about data entries for now. It doesn't prevent you from having more than one indexes for data entries, for different kind of data entries. Cluster index and unclassed index only constrain the ordering of your records, but not the ordering of different kind of data entries. Does that answer your question? Okay. What about a hash index on day and RNA? Will this be useful? Well, the general answer is no. However, if you know the name domain is small, if you only have a few names, then potentially you can still use this by applying the trick I talked about earlier, which is augment your search condition date less than that with name equal to 1, name equal to 2, name equal to 3. And check all of them.
Can the same technique be applied for the B plus 3 on hardening and date?
Potentially you can, yes. I mean, first of all, if it's this, there's no, yes, you can apply that trick, but you know, it doesn't gain anything by doing that. If it's this, yes, it does apply. However, again, it goes to how efficient of that approach, right? It boils down to that. So that's one approach. The second approach, leverage on the fact that, okay, let's go with this example I have here. The second approach for selection says, okay, yes, you can go with one access path. But if I have more than one access path, can I somehow utilize all these access passes? That's very intuitive, right? In our real life, of course, in real life, we cannot do that because we human have only one brain and we have one body. So if I want to come to this lecture hall, I cannot say split my body into half, and one go from MEB, one go from the basement tunnel, and then meet here, then merge back. And if it's possible to do that, I will do that. You know why? Because you don't know which lane is having less traffic at this moment, right? Do you see what I'm saying? But computer can. They have multi-core, multi-threading, and all that. They can easily do this. So that's the observation of second idea, which is, you know, if I have more than one access path, don't go with the most selective one. Rather, you know, do both, and then do an intersection of the record IDs in the end to find your final answer. So using this example, what I can do is I can execute this query over this and execute this query over this in parallel. I'm not going to do them in sequential. Obviously, I'm going to do them in parallel in a multi-threading approach in today's multi-core system. That's fairly common. So I do that, and I do that. Then what I do, one thing to remember is there's a subtle difference is in the earlier approach, when you go with one selective path, the most selective access path, you have to retrieve records. You cannot retrieve just the record IDs because you need to apply the remaining conditions, and for that you need the actual record. Oftentimes, of course, database engine will do optimizations by projecting out only the necessary attributes, meaning you record maybe A, B, C, D, E, F, G, many attributes. And when going with one access path, I will put that out those records satisfying your condition and the attribute for the remaining conditions. So in other words, I will put out A, B, C for all the records satisfying A and B conditions. I will not put out records as A, B, C, D, E, F, G. Okay? They will always do this trivial optimization. However, in this case, because you are going down two access paths and you are using another critical observation is we are using CNF, conjunctive normal form. What that means is by the end of the day, when you get back from two access paths and you're dealing with CNF, meaning that you will do an intersection because you're dealing with an AND condition, not an OR. So you're doing an intersection. I mean, you can, of course, retrieve all the values for all attributes needed for your condition and then do the intersection over that. However, that might be expensive because each record might be, at this point, 100 bytes or something like that. So if you have 1 million in each set, you are intersecting two sets of 1 million times 100 bytes. You know, that's gonna be expensive. So what people usually do is if I do the second approach, I will go with retrieving only the record IDs, which is a single value. Regardless how expensive your condition is, how many attributes were involved in your condition, I retrieve only the record IDs, which is a single value. Then I do the intersection. Hopefully, after the intersection, the size of the final answer is so small, and at this point, I can just use these record IDs and go and fetch those records one by one. You follow me? And this is particularly useful because in commercial database, as I said earlier in last lecture, by default, they always build a cluster index, or what they call primary index on what? On primary keys. And oftentimes, more than 80% or 70% of time, the primary key for a table is on an auto-increment attributes like RID. So if you intersect and get the RIDs, retrieving record by RIDs is very efficient. That's what I'm trying to say. Of course, this approach sounds like the second approach is always better, right? You're doing in parallel, you do this intersection, reduce size, and why not always use it? Well, the tricky thing is, the truth of the matter is, it's not the case that this is always going to be better. Why? Can someone tell me why this is not always better? I mean, it sounds like it should be better all the time, right? You're using multi-core to do all these fancy things.
When the size of the intersect result will be more than we can fetch because it's not smaller after the intersection of the two parallel queries.
Well, you have to be careful here because the intersection gives you the final pure answer. That will be the same as the size of the first approach, the final answer, because they give you the invariant here is you get the final output, whether you are using approach 1 or approach 2, which is the same. That's one factor. That's actually a question I plan to ask you. How do you do intersection over two sets, by the way? Can someone tell me that? Alex?
You have to apply all the remaining conditions for both patterns.
You have to apply remaining condition. Well, no, because that's precisely what's awarded in the second approach, meaning each condition is involved in one of the access paths that's being executed in parallel. So by doing this intersection, already guarantee that all conditions have been checked. So you're safe. You don't have to apply any post-version step. That's precisely one of the savings of the second approach compared to the first one.
If you can keep a larger set in the hash map when you get it, then you can check from the other one. You can do a linear scan and just check in constant time.
Fantastic. So that's one approach. I will defer the discussion on this set intersection problem later on because this has strong connection with joins. You may wonder how set intersection is related with join. Think about natural join. I claim if you have a solution for natural join, you can do set intersection. Okay? Think about that for just a few seconds. Then later on we will have a detailed discussion on join, then we'll come back to this problem. But excellent. Set intersection might be expensive, but that's one factor. But suppose I have a very efficient way of doing set intersection. What is another? What is a catch? What is a catch? This is not really the fundamental reason. What's the catch?
Memory and disk convention?
Yes, that has some factor as well. I mean, because you are doing multi-core execution, cache contention can be an issue. However, that's still not the catch. The catch is what I'm gonna show you next, which is the catch is if you do access path in parallel, you may run into this problem. Let me show you. Let's say this is my access path 1. And suppose this is my original data. This is my D. Is that okay? And my access path 1 will fetch, let's say, this part. So that will give me this output. Is that okay? Keep in mind we're doing C and F. Okay? By C and F, once I know this, you know what? You know the final output, final answer must be what? Where is final answer? Can the final answer be like this? Impossible, because we're doing C and F. Critical, okay? So the final answer, because we're using C and F, the final answer must be what? A subset of this. What about AP2? Well, your AP2 might be, well, you know what? Might be this. Now you tell me which is more efficient. One is doing them in parallel, then intersect, versus you tell me which is more efficient. Obviously, this is going to be efficient. So now the real catch is, if you execute multiple access paths in parallel, you may be retrieving a lot of unnecessary records. This is what I call unnecessary records. You follow me? When is this useful then? Well, it is useful when you have something like that. When you have like either part, none of the access path is actually selective. None of them is actually selective. Then doing them in parallel, the intersection will be typically will be useful that going to with just one of them. So again, you may wonder, okay, now I know this. Who's the boss? Who's going to make the call? Well, the query optimizer will make the decision. All right, so that's that. Let's continue. What about project? Yeah.
At what point of time it decides that it has to
Sorry?
At what point of time it decides that it has to go sequentially or parallelly?
Well, the typical workflow is user submit a query in SQL. It goes through a pattern, pass that into relational algebra query plan. Then the query plan will go into a query optimizer to find an effective plan, which we skip for now. So we skip that step. Now we're in the query evaluation step, which is we talk about all different ways of implementing our operator. And once we understand all of this, we will come back to the query optimizer, where that decision will be made. And now let's talk about projection. Projection, the main thing about projection is whether you need to do duplicate elimination or not. Because in SQL, by default, projection does not remove duplicates, like we said earlier. But relational algebra does. If you want to remove duplicates, you add this keyword called distinct. So the basic idea of duplicate elimination is to use sorting or hashing. We can use either sorting or hashing. In this case, let's say we can. Now we know how to do this, right? In the earlier discussion, we just said we do sort or hash. Now we can actually analyze this with special numbers. So you scan R, reserve, and retrieve only the needed attributes. Sort the resulting set, and remove duplicates that are coming next to each other. One question I have is why you bother to do the first step? Why do you bother to do the first step? Why you only put out the needed attributes? What are the needed attributes, by the way, in this case? SID and BID, right? So why you do that first step? Well, the point is, what is in the reserve? Both ID, serial ID, and date. And date typically is expensive, right? In terms of number of bytes needed. You know, so let's say you are sorting 100 numbers, 100 elements. Which is going to be more efficient? Sorting 100 integers or sorting 100 strings? Obviously, sorting 100 integer will be more efficient because it uses less number of bytes. So that's the purpose of step number 1. As read the records, keep only the needed attributes and sort. Okay? But why my cost is this? Well, the reason is I'm going to go over this cost analysis with you all together. And keep in mind, we're using the reserve table, which has this setup, right? Reserve is okay, that's the setup I have. So what is my cost analysis? So what is the cost of this query? What is the cost of this query given this information? What I'm doing right now is actually simulating the behavior of the query optimizer in the database engine. This information are available in what we call metadata. And the query optimizer will read this data in and evaluate how costly a particular plan is, and then decide whether I want to go with that plan or not. Okay? So what is the cost of this plan? Well, the idea is you read in all the pages, that's 1000 IO right there. Then you remove unnecessary attribute and keep only those ones. Let's say we know that these two fields occupy 25% of the record, and date occupy the other 75% of the record. Then the 1000 pages will become 250 pages. 1000 pages become 250. Why? Because there are no selection condition in this case. All records are still kept, but each record shrinks to 25% of its size, so the total number of pages will be reduced to 250 pages. And you need to write them back to this. And then you do the sorting. And what is the cost of sorting? Well, let's say we have 20 buffer pages. 250 pages with 20 buffer pages, how many passes we need to sort them? Let's say, so that gives me about 10, 12, 13, right? 13 rounds. So you pass 1, pass 2, because I can merge 19 rounds in a pass, I only have 13 rounds in pass 1. In 32 passes, I'm done. And that's why you see this value here. But what about the final 250? Well, you need to linear scan over it and remove the duplicates. You may wonder, why don't you add, shouldn't there be another cost right here, which is write the output, which is value some number less than or equal to 250, right? Cannot be greater than this. In the worst case, equal to this. but most likely will be less than it. Why don't we include that? The reason is, typically in cost analysis, we don't involve that because no matter which pass you do, that's a common factor. Everybody has to do this, no matter how you does this. Even the almighty guy up there, he has to do this as well, right? You need to write out, so we don't consider this as part of the cost analysis. Okay?
So for duplicate records, is it feasible, instead of storing the separate records, can you just store with each record a number indicating how many of those records are there?
Well, but in order to do that, you need to do the sorting first, right?
Yeah.
That's what we're doing. You can actually improve this by modifying the external sort algorithm. Why? The reason is, if you think about it, this and this and this can actually be combined. Okay? This, and this can be combined. What do I mean by that? In pass 0 of my merge sort, I read 100 pages in, but I read them in 20 blocks, right? Because my buffer size is 20. So what I'm going to do is as follows. I'm going to show this, right? So this is my buffer, which is 20. This is my sorted pages, 20. So in this approach, I load 20 pages in and so on and so forth, right? What you can do is, I load the first page in. In the process of loading it, I remove unnecessary attributes. So one page becomes what? It's only 1/4 of a page. In other words, every 4 pages will actually give you just 1 page of data. Why? Because I'm keeping only the BID and SID, which is 25% of the record length. So every 4 pages become 1 page. Every 4 pages become 1 page. Every 4 pages become 1 page. So with 20-page buffer, I can actually get what? 80 pages of data. Then what I do? I sort them. You don't dump to disk and load them back in to sort. You sort them now. Why later? Then you sort them and dump. And that gives you a run of 20 pages. You follow me? And 1,000 pages with 80 pages going to a run, that gives you, I think it's the same number here, because that's kind of like 4 times on both ends. So with this approach, you get, what's the cost analysis of this approach? Now, you read in 1,000 pages, you write, how many pages you write in the end? Well, you write 250 pages. Why? You can go the hard way, which is, okay, 80 pages become 20, then I write 20 pages, then I have to do how many such 80 pages, translate to how many 20 pages, mathematically complicated. But you can do a simple analysis, which is ignore all this complexity and argue, at the end of the day, I have to write this data to disk. And I'm writing 25% of the data, which is 250 pages. And then I know, using just another pass, I will sort them. I'm done. So another pass is 2 times 250, then plus linear scan over them once more. Okay, so that's a cost. Is this the best you can do? The answer is no. You can do even better than this, no matter how. I argue you can actually remove this last step as well. Why? Because the key observation is, in this one pass, I guarantee to sort the data already, because I only have 13 rounds, and I have 20 buffer pages, so I can merge 19 rounds at a time. So I do get the global sorted order in this path already, which means I can do the duplicate elimination on the fly while I move those cursors from those 19 rounds. Actually, not 19 rounds, 13 rounds. I only have 13 rounds to merge, even though I can potentially do 19. So while I'm merging those 13 rounds, I remove duplicates while checking that. In other words, if you see some duplicate value from these different rounds, instead of pushing the value to the output buffer, you simply skip that. Until you skip so much, you see the next value that's supposed to go to the output buffer that is different from the last value you push to the output buffer. Only then you push to the output buffer. Otherwise, you only advance the cursor without pushing anything to the output buffer. So the total cost becomes this. And actually, not even have the 2. It's only 1. You do like this. Because I don't even have to, yes, you have to write the output, but my output is not the sorted output, but sorted output without duplicate. By my argument earlier, we don't count that as part of the cost. So my total cost becomes this, which is 1,500. You cut by almost half of this. And there's another approach, which is to do duplicate elimination by hashing. I'm going to skip this, which is, you use one of the hashing algorithm we talk about. One of the hashing algorithm we talk about, which is what? Two-phase hashing or hybrid hashing. You use one of them, you hash, and during the hash process, there are 2 ways of doing this. One is you do the hash first, then you go and use the in-memory hash table either from the hybrid hashing in the first phase or the in-memory hash table you built from the rehash phase to remove duplicates. But you can do optimization just as what I have done here, which is to combine the duplicate elimination into the hashing process itself and remove duplicate on the fly. You can do that as well. Okay. Now let's talk about joins. Join is interesting. I'm hoping I can finish the discussion of join today. Right? So I'm going to focus on natural join, which, in other words, natural join is the same as, almost the same as equality join. Right? To give you a quick discussion on the difference between natural join and equality join. Right? What is the difference between natural join and equality join? Well, they're almost the same. So when I write, this is the natural join. Suppose the only common attribute is A, then these two are almost the same. You follow me? Except what different? Except that this attribute equal to only one A, right? That's the difference. If you think about from the query evaluation point of view, now we understand this better. From evaluation point of view, this makes almost no difference. Because this projection is not, duplicate elimination is not involved here. So doing this projection or not doesn't really impact your query evaluation. Okay? So we will focus on, that says we will focus on the discussion of equality join. Because equality join gives you a solution for natural join automatically. Okay? And I'm gonna write these assumptions on the chalkboard, which is And we are considering this very simple join, right? Very simple join, right? On the set ID. How do you do this? I think I'm going to talk about 5 different algorithms, right? 5 or 6. The first one, I think everybody, if you know nothing about database, but just as a computer science student, the trivial solution is to do a nested loop-like approach, which is for each reserve, I go through every single record in sailors and check whether they satisfy the condition or not. The nested loop, the order of the nested loop doesn't really matter. You can also do for each sailor, I go through every record in reserve and check the condition match or not. Okay? So that's this. The tricky thing is, what is the cost? What's the I/O cost of this approach? Well, the I/O cost for this first one is simple nested. What is the I/O cost? Well, for every record, let's say we do for every record in R, we scan every record in S. So for every record in R, how many records in total in R, which is PR and M? For each of this, I need to scan every record in S, but because we're using a buffer manager, the I/O cost is not, rather it's simply this, because I'm using a buffer manager, so I'm loading a page at a time. You pin page, right? When you implement product tool, you pin, and so on and so forth, right? And so that's the cost. But remember, by the end of the day, when you have finished this nested loop, what you have done? You have read every record in R once, which is the I/O cost of that. Okay? Or you can flip the order of your nested loop. So for every record in S, which is this many in total, I'm going to scan every record in R, but the scanning cost of that in terms of I/O, not in terms of number of CPU operation you have to do. In terms of I/O, for every single record here, I need to scan through every single page of R. That gives me a total number of this many I/Os, because for every record, I need to scan through all pages in R. By the end of the day, when I finish all of this, I have read this many records in N pages, so I have another N. But in reality, what's going on is, if you think about this, you read the first page here, then you scan N pages. Then you read the next page, you scan N pages. You scan M times wrong thing. PS times N is what? PS this times N. Okay. So to understand this, what's really happening is, for this N pages, right? For this N pages, you load the first page in, which has PS records, which give you MIOs, because for each one of them you scan through the N pages. Then you load the second one, PS, N. So on and so forth. And by the end of the day, you have N of PS M. So that's how you understand the formula. Okay? So that's the total cost for simple nested loop. And if you plug in the numbers we have, this is huge. Using our example, you got to answer this query, you got, I don't know. I mean, if you can do 10 milliseconds per I/O, which is pretty much what the disk can do. Maybe it's slightly faster than this, but typically I/O cost for disk today is in the order of milliseconds. A few milliseconds, some are faster, some are slower, but it's in the order of milliseconds. If you use this approach, well, good luck, right? You can do the math, this will take a long time to finish. But you may argue, this is kind of stupid, right? For every single record, you scan the other page. Then the next record coming in, you scan everything. Can you do something better by remembering the scan you have done, right? That's kind of the trick for the second approach, which is a very simple optimization is you need to do page nested loop. Page nested loop. Page nested loop. The idea is actually the same. You still do nested loop. I load the page from the first table, the first page from the first table, instead of the first record from the first table. Then I scan through the other table. So I do exactly the same, but now I get rid of this factor. I hold a page of data in memory rather than a single record in memory. The idea is, once if I have this page in, while I'm scanning through the other page from the other table, I'm scanning them through. Okay? So I take one by one. When a page is here, I will do a in-memory nested loop over this record, but that doesn't incur any I/O for me. That's what I'm doing. So the total cost in this case is now this becomes interesting compared to that. Why? Because this tells you the order actually matters. Because this term is exactly the same, but this is not. And typically, in most database systems, the join is between a small and a big table, which means they are not in the same order. They are not in the same order. They are not in the same order. Either one is the case, typically in a database system. So the idea is what? You want to use the smaller table as the outer table, meaning the first loop as the outer loop. Use the smaller table as the outer loop, always. Okay. And by doing this trick, we can reduce the cost to this much. This is much, much smaller than simple nested loop. Now let's continue. If I have index, I should be able to use index to speed up my query processing for join, right? So how do I use index? Well, the idea is still do nested loop. I'm gonna erase, okay? Let's erase the words ever. Right? Nobody will ever use this actually in practice. So index in nested loop says for each record in R, since you are doing equality join, right? You don't have to, if you have an index on S, suppose I'm looking at, suppose that's my thing. And this index can be a tree index or hash index, doesn't matter, a hash or a tree. Both can be used because we're talking about equality implementation. So what I do is I scan through every record in R, and for every record in R, instead of linearly scan through S, I will simply use the index to fetch only the records match the current value of A. Each record in R has a specific value of A, right? I will use this value of A to do an equality search using that index over S and only check those records. So that's this. And what is the cost of this approach? Well, by the end of the day, you have to scan all data in R, that's give you MIOs. And for each record in R, which is this many records in total, you are doing an equality search using the index. So quality search cost over T. That's it. Okay, so that's the cost of this approach. Okay? Is this better than, it's definitely better than simple nested loop join. Is this better than page nested loop join? Not necessarily so, right? Maybe. Why? Because this could be a huge number. This could be a huge number. Of course, there's some optimization we can do here, which is if A is not a key, meaning that you may have a lot of duplicates on the A values, you don't have to do this equality search on every record. You only need to do this equality search on every distinct A values. That might give you some savings.
So here again, we want M to be the smaller of the tables, because then, you'd be using the index on the bigger table, and you have a smaller multiplier there.
Well, the answer is it depends actually, because this, it's not sure which table we want to use as ultimate, right? The cost is it depends a lot of depends on the number of problems you have and the cost of searching on that index. Maybe one has a hash, one has a tree. The hash maybe wins out,
Right.
even though you have less number, something like that. Now, there's an example I'm going to skip. Okay? You can read yourself. Now let's move on to the next algorithm, which is a little bit more involved but still very simple, which is called block nested loop join. A block nested loop join is an extension of page nested loop join. If you think about this picture here, you're holding one page from R and scanning through the page from S in the memory. But the reality is, you don't have just one, and you don't have just two memory in the buffer. This is buffer, right? You follow me? The buffer is much bigger than 2. So how can you utilize that? Well, you use all the remaining pages to hold page from all of this are from R. Then you linear scan through S. And of course, you need to have an output buffer. And when this page is loaded in memory, you do a nested loop between all of this and that. An in-memory nested loop of all of this and that. And produce output to the output buffer, and whenever output buffer is full, you dump to the disk emptiness. And when you finish scanning every single disk, throw away this, load the next few guys, and do it again. And what is the few guys? Well, if you total is B, you reserve one for output, one for input. How many guys you can fit here? B minus 2. And how many times I have to do this? You have to do this many times, and each time you're doing this, you scan the entire S once. And by the time finish doing all of that, you read these pages from R exactly once. Of course, you can do this the other way around. And similar to the page nested loop join, for block nested loop join, if you look at the formula, you always use the smaller one as output. Okay? So that's block nested loop join, which is now let's look at the more involved ones. There are two more that's more involved. One is sort merge join, one is hash join. Sort merge join. What is sort merge join? Well, the idea is if the tables are sorted by A, intuitively that should help you, right? If they're sorted by the join attribute, you should be better off. You should be, right? The question is, how do I leverage that? Well, the naive idea is sort R, sort S. Of course, based on what? Based on the joint attribute. Based on the joint attribute. Then what I do? I have to draw them up. Okay, what I'm going to do next, I'm going to label different regions from R and S according to the value of A in that region. The value of A in that region. So I have one color. I don't have color, so I'm going to draw using different fill patterns, right? Different fill patterns. So suppose these are this is and this part is okay. What does this mean? This means records with A equal to okay. Of course, those records, the attribute of those records are, the values of those other attributes on those records can still be very different. But I only care about A, because I'm doing a join over A. What about S? What's the picture for S? Wow. It doesn't have to start with star, huh? You don't have to do, for little kids, they always do what the others do. But when we grow up, we don't. I'm running out of plans. But now I have I also have some additional really run out of okay. Okay, now what I do? One thing I know for sure, they are both sorted. Because I sort that. So what I do? Can you calculate what I do? I introduce two cursors. One thing I know for sure about this will be smaller than this, because this is here, right? So what I do? I check, is this smaller than this? Yes. Move all the way to here. Is this smaller than this? Yes. You don't have to do anything, just check and move. Now what happens? They're the same. When they're the same, what I do? I do an in-memory nested loop join. And then what I do? The next step is critical. Not only I have to move this, now I need to move this as well. So I will move this to here, and I will move this to here. Check. Now this is smaller. This is bigger. Now I have a circle here. I know this must be smaller. So instead of you have to stop, now it's my turn. So I will move. You have no square, but it doesn't matter. I know this will be smaller than I do have circle. So I will move. Then at this point, what I do? and you continue. Suppose each of this block is not too big and can fit in your memory. Typically, that would be the case. Your entire table might be huge, but each of the blocks is smaller, can fit in memory. Moving these guys forward, this whole thing takes only linear IOs on both ends. Because once you are in a region, you are doing in-memory nested loop join without any additional IO cost. So the total cost of this, the third step is simply, so the total cost is the IO cost for sort R, IO cost for sort S, plus linear scan over two tables. So that's the cost of this. You can read it, whatever over there. There's an example of this as well. And what I'm going to do on next lecture is that think about how we modify the sort process to do duplicate elimination. So we remember that there's a huge difference between here and here. This is sort, duplicate elimination, and this is sort and duplicate elimination together. So that implies, is there something that do sort / join at the same time? The answer is yes, but it's not as trivial as this. I will discuss that. And in fact, this question mark will reduce this whole thing to which is fantastic. But there's a condition, which is the max of the two. And now this condition looks familiar, right? This condition is what? For hybrid hashing, what is the condition for you to do it in two paths? Right? For hybrid hashing, there's only one table. But now we're looking at the max of the two mass less equal than. What's the connection? All of that, we'll talk about that next lecture, okay?